Okay, so what we'll do is we'll today look at few advanced instructions related to MCS 51, and we'll see that with some examples. Few of the instructions shown here will are not covered in this lecture. It will be covered in the part two of this particular lecture. Now let's have a look. What are the instructions that we are going to? What is the conclusion that we are going to draw today? The conclusion that we are going to draw today is the implementation of lookup methods. We can then see the instructions which are used to communicate with the external data memory. Then we will have a look at the interchange bytes by a single instruction. Then we'll have see the examples of using MUL or div instructions which are used for multiplication and division on unsigned numbers. Then we will go to get a proper entry point among multiple subroutines. We'll use some instructions which can be used to jump from different locations or can be used for multiple subroutines. Then we'll have look into the instructions which are basically used for BCD arithmetic. Then these are the instructions that we are going to cover today, which we call advanced instructions related to MCS 51. Now, what are the instructions that are being shown here? The instructions which are shown here are move C, move X, XCH, XCHD, MUL, div, DAA, jump, RETI, swap, and JBC. In this particular section, we may be seeing few of the instructions in the next part of the lecture. So let's have a look at the instructions with examples. Now, what we are going to see right now is the advanced instructions related to move C instructions. See, you'll have to listen to this very carefully, as these instructions are advanced and are bit. You may get confused with the other instructions, so it's better to have a very clear understanding of this particular instructions. Now, in move C, what it is, this loads the target byte from the program memory to the accumulator. Okay, so there is a target byte which is available in the program memory and it is loaded to the accumulator. Fine. To find the target address, we do that by adding the content of the accumulator with a 16-bit base register, which may be the program counter or it may be the data pointer counter. Sorry, data pointer register. So we have to be very careful that there is a target byte that we have to get from the program memory. Please remember, we are we are fetching the target byte from the program memory and loading that into accumulator. This is bit different from others. Again, I'm saying we are trying to load a target byte. Target byte, in the sense, is the byte that we want to fetch. We are calling that the target byte. We will take that from the program memory and put that into accumulator. So how are you going to get the target address of the target byte? It is obtained either by adding the present content of the accumulator with a 16-bit base register. Any 16-bit base register where it can be a program counter, the 16-bit base register can be a register, can be a program counter, it can be a data pointer register. So there are two registers, 16-bit registers that we will consider. One is the program counter, another is the data pointer register. Now let's move on. Well, this type of instructions come under the indexed addressing mode. Okay. Now, Here are the two instructions that we are going to deal with. The first one is move CA, comma, @A plus DPTR. Now, in this particular instruction, you can very well see that @A means there is a part of the, actually the target byte is somewhere in the program memory, and the address that we are going to get for the target byte is available by adding the present content of accumulator along with either the DPTR or the PC. But in this case, in this instruction, which is move C A, comma, @A plus DPTR means content of accumulator now will be added with the content of the DPTR, data pointer register, and the thing that we will get, a 16-bit content that we will get, will be the address of that target byte. Okay. Similarly, the instruction is very similar for the next one here. The present content of accumulator gets added with the program counter, and then it becomes the address of the target byte. Fine. Now let's have a look at the example. Now in this case, we have move CA, comma, @A DPTR. Its operational code is 93 hex. Fine. And it's a 1 byte instruction. Very well, we can see that this particular thing is a 1 byte instruction. So 93 is the operational code. Fine. Now in this case, the DPTR is the base register, and it contains the 16-bit address which is added to the current content of the accumulator. Fine. Now, in this case, we can very well see that we have content 03, which is initially getting added with the DPTR. Now, DPTR here is 01FF. Okay, so 01FF is added with 03. Mind it, it is the unsigned integer. It's treated as unsigned integer. So whatever you have in register A, that is the accumulator, it gets added with the content of DPTR, which is our base register, 16-bit base register. And what we get, see here, it's getting added, and what we get here is the location 0202. Why? Because DPTR was having 01FF, and adding 3 to it, 1, 2, and 3, it will give you the location 0202. Now the content of 0202 will be put into the register A. Fine. So the here you can see what I just said has been written here. That is the initial content of accumulator. Again, I'm repeating the meaning of this particular instruction. Initially, the accumulator was having 03, and the base register, which is the 16-bit base register, here we are considering DPTR. The DPTR is having 01FF, and we are adding the initial content of accumulator with 03, which is now it was 01FF, it gets added 3, so 1, 2, and 3. So present location is 0202, and the available byte here will be copied to the register A, and the initial content of register A will be destroyed, and the new content will be added to the accumulator. Fine. So the next instruction that we are going to see is related to the program counter. Now it's bit again we'll have to listen to this very carefully. Now It is the similar fashion, but only problem with program counter is the program counter, once the instruction is fetched, it automatically increments to the next instruction. The address of the program counter automatically increments to the next one. So the next address that is presently in program counter will get added with the content of accumulator. Let's see how it happens. See, in this we have also seen that, note that at the time of this addition of the content of accumulator and the program counter, the program counter will be pointing to the first byte of the next instruction. So you'll have to be very careful in understanding how this particular instruction works. So the addition does not physically change the value of program counter. So again, we have to understand that once the instruction which was being fetched by the program count by the microcontroller, the program counter automatically increments to the next instruction. It points to the next instruction. So the next instruction value of the address and the initial value of the accumulator will get added. Let's see how it happens. Let's see here. See, in this case, the operational code of move CA at the rate APC is 83. Again, it's a 1 byte instruction. Now, it was loaded into the location 01FD. At 01FD, what we'll do is the program counter automatically increments to the next. So, after the fetching of this particular instruction, the program counter value is 01FE, which is evident here. 01FE, because every time a program counter is used to fetch an instruction, it's automatically, once it is fetched, it automatically increments to the next location, which is evident from this particular situation. Now, this 01FE gets added with the initial content. Remember, it is the initial content. The content which are shown here are the initial one. So 04 and 01FE both are getting added. So once they get added up, it moves to the location 0202. Obviously, the program counter value was this. So once it get added with 4, 1, 2, 3, and 4. So the present location will be 0202, and then that particular content will be transferred to accumulator, and the initial content of accumulator will get destroyed. Okay, so it is evident from this particular sentence that this 0202 hex is obtained by incrementing the program counter to the start of the next instruction, that is 01FE, and then adding 04 to it. Fine. Now, let's move into the other instructions, in which we have move X instruction. Now, move X instruction communicates between accumulator and external data memory only. Please be very careful in addressing this particular situations. This particular instruction, which is move X, it communicates with the external memory. It doesn't communicate with the internal memory at all. So the microcontroller is having two internal memories. One of the internal memory is the program memory, another internal memory is the data memory. So whenever, as per our requirement, we communicate the instructions with the available data and instructions in the program as well as data memory. But when we are talking about this type of category instructions, these instructions only work with the external data memory. It never accesses the internal data memory. So let's have a look at it. Fine. So again, there is no scope of communicating with any other type of memory, that is the program or the internal data memory, through these instructions. It is only for the external memory. The, the instructions are move x a comma at the rate ri. Now at the rate I here means it can be either r0 or it can be either r1. So as we know, the hash bank 0, that is the bank 0, register R1 and register R2, register R0 and register R1 are the only registers can be used for as a memory pointer. So in this case, that is the move x a comma at the rate ri. What it will do is it will load the accumulator with a content which is a 8 bit content or a byte from the external memory. From the external memory using indirect bit addressing with the help of at the rate ri. Similarly, in this case, the life becomes a little bit easier where the address of the external memory, always remember the address of the external memory is always 16 bit. Okay, it is always 16 bit. So you have to use a mechanism to address that particular 16 bit external memory. Remember, the the data memory inside the microcontroller can be addressed using 8 bits, but not the external memory. External memory is addressed using 16 bits. So the microcontroller needs to generate a 16-bit address in order to fetch any information, any data from the external memory inside the microcontroller. So in order to do that, we will have to use certain techniques which is highlighted in the next section of this particular lecture. You see here at the rate move x a at the rate dptr is an instruction which is held by the data pointer register, where already there is a 16-bit address available inside it. But the life is not that easy when we talk about R0 and R1, because R0 and R1 are capable of handling only 8 bit. So rest of the address has to be generated and pushed out of the microcontroller using some port. See, there are four ports: port 0, port 1, port 2, and port 3. So somehow we have to send out a 16-bit address to the external data memory. So we will see that how to do that. Now, these instructions above two, this is the move xa at the rate ri, move xa at the rate dptr. Both these instructions load the content from the target memory. Now, in this case, it is just the reverse. Okay, so here from the accumulator, the 8-bit content of the accumulator gets loaded into the target memory. So, vice versa. So, these two are for getting the information from the target memory, from the memory to the target, which is the accumulator. And here, the content of the accumulator, which is the 8-bit content, is transferred to the target memory. Okay, so let's see how it is done. In the first instruction, which is move x a comma at the rate r0. So it is a 1 byte instruction. So its operational code is E2 hex, and E2 hex is written in the program memory. So once the instruction is fetched, now the microcontroller knows that it needs to access the information from the external data memory. So again, we have to remember the external data memory that we are considering is having a 16-bit address. So we will have to somehow use a mechanism to address this particular data memory. So how can we do that? Okay, the addressing architecture of internal data memory is 8-bit. I have already said that. To generate a 16-bit external address, to generate a 16-bit external address as shown on the right hand side, we either have to use the help of this R0 or R1 or the DPTR. Okay, so in this particular case where we are considering R0, the lower 8 bits of the external memory address are stored either in R0 or R1. Suppose we want to address this particular location, which is 1FF9, which is the external data memory. Now 1FF9, the F9 part, the lower address is stored in either R0 or R1. Now this is out. Now this particular F9 is sent out to port 0. Remember, port 0, port 2 are the port 0 can be used as address data bus where it can act as the lower order address bus, and port 2 can be used as the higher order address bus, doesn't matter, but port 0 acts as the lower order address bus. So you'll have to somehow use to send the information or the address, that is F9, out of port 0. Fine. Now to generate, and in this case, we have to assume that the higher byte, namely 1F hex, has already been generated either to any one of these ports. That means either you send 1F through P1, port P1, or port P2, or port P3. See, port 0 is used to generate only the lower order address bus, but port 1, port 2, and port 3 can either be used as any one of the ports can be used to send the higher byte of, that is, higher byte is the 1F. So it can be used to send through this any one of these ports. So upper byte of the address is available through P1, P2, and P3, and the lower byte is available through R0, which is F9, through the port P0, and it is then used to address the external data memory. Okay, so now let's move on to the next. the the complete 16-bit address, that is 1FF9. We are now looking into the instruction which is movex a at the rate dptr. Now it's very easy. You have the instruction, you have the address in the dptr, which is 1FF9. So this is emitted through port 0, that is the lower part will be emitted through the port 0, and the higher part can be sent through the port P2 to the external data memory. So life here, it's bit easy when we use the DPTR, because we can directly load the address into the DPTR. It's a 16-bit register, so the lower byte can be sent through the port 0, and the upper byte here is sent through P2, the port P2. So we will be able to address the location 1FF9. So it's a similar technique. In this example, we have shown 1FF9. You can use any of the location using these instructions. Okay. Again, remember, these are the instructions which can only access the external data memory. They cannot be used to access the internal data memory. Okay, there is no need in this case to entrust any port to output any of the address bytes. Okay, because in this case you are already having the entire 16 bit address in the DPTR. Okay. In the previous example, we were taking one of the ports to send the 1F, but in this case, we have to send everything through the ports itself. But in the previous case, we had to send 1F initially from that particular port. Then using R0, R1, we had to send the lower byte. So in this case, it can be directly sent from the DPTR register. Now, the other thing is just the reverse of it. In this case, F3 is F3 is the 1 byte uh, operational code of move x at the rate R1. From here, we are actually sending the information that is inside the accumulator into the location 1F9. So in this case, again, the F9 is loaded in the here we can see we have used R1. So we are using R1 register, and we are using as in association with any of the ports which will be having 1F initially loaded into it. So port 0 and any of the ports can be used to send 1F, and hence the 16-bit address is available, and those 16-bit address will point to a memory location where the accumulator content, whatever be the accumulator content, it can be anything. It can be 8-bit, any data is stored into the external data memory. And remember, no flags are affected, and the content of register R1 remains unchanged. The content of this particular register remains unchanged even after the instruction is executed. But we have to remember one thing: we can change this as per our wish and as per requirement of the uh, program that we are using. Fine. Now let's have a look at the other side of it. In this case, we are using DPTR as the base register. So the content of accumulator will again be transferred to the designated location whose address is presently inside the DPTR, where the DPTR will be linked to the lower part will be linked to P0, and the upper part can be sent through another port which is P2. So in this case, the target is the external data memory and the source is the accumulator. So content of it will be stored into the external data memory whose address is in DPTR, and DPTR is again linked with port 0 and port 2. Okay, now let's move on to the next instruction, which is XCHG. In this case, the instruction interchanges the byte variables between the accumulator and any other location. Okay, so in this case, the let the this is XCHA and Rn means R0 to R7. This is a register direct, so interchange the accumulator content and the register content. So the content of this and this will be interchanged. And in this case, the next one, XCHA direct, here means the content, already we have been given the direct address. So direct address may have some content, exchange it. Now in this case, in this case, we are having XCHA at the rate RI. Here, the register here, the at the rate RI means we will have to consider register 0 and register 1. This will act as the memory pointer and the content will be copied to accumulator. Now let's see how it happens with an example. Now, in this case, we are considering XCHAR4. So, it is a 1 byte instruction, and the the operational code is written across this program memory. Once this is fetched, the microcontroller will now understand that it has to go for an exchange operation. So in this case, the R4 content of R4, obviously by default register bank is hash 0 until and unless you change it. It will be R4 of the bank 0. So the content of this particular register R4, it gets interchanged with the content of the accumulator. So the accumulator content will now move to this particular location, and the content of here will go to the accumulator. Okay, and in this case, no flags will be affected, and execution would take only one cycle to complete this 1 byte of instruction. Now let's move on to the next. In this case, we have the instruction XCHA, comma 30. Now it's a 2 byte instruction. So to write that particular instruction, you have to write it in the program memory, which is C5 is for XCHA, and 30 is this. So we are providing the direct address of the content inside the instruction itself. So in this case, what we will see is there is a the content of the location 30, which is a scratchpad area of the internal data memory. Since we know that just below that is the bit addressable area, and just above that is the general purpose of the scratchpad area. In the scratch area, you can the content of corresponding to the location 30 gets interchanged with the accumulator. Okay, so interchanging operation takes one cycle and no flags are affected. Fine. If any port is addressed, then the data would be taken from its input pins and not from its output latches. Now you'll have to remember, if anything is any port is addressed, then that particular data will be taken from the input pins. Fine. It will be taken from the input port when the ports are acting as input. Fine. Okay. Now let's move on to the next part where we have XCHA at the rate R1. And we all know that that at the rate R1 means that it has to be the register R1, okay, which is the by default register of bank 0, which can only be used as the memory pointer. So in this case, what is happening is, suppose the R1 register is having 30, so that will act as the memory pointer, and the content of 30 will now get exchanged with register A. Similarly, it is the same with R0, where R0 is having the contents address. So it is address is given as 30. So the content of 30 will now get interchanged with accumulator. Fine. Okay. Now let's move on to the next part where we are considering the multiplication instruction. Now, in the case of multiplication instruction, we have MUL AB, which is nothing, which opcode is A4H. And this A4H means multiplication of the content of accumulator and the content of register B. Register B's direct address is F0, and register A's direct address is E0. These are special function registers. Now, in this case, the again you have to remember one thing. This is a unsigned operation. This is not a signed operation. So multiplication of two unsigned integers located in accumulator and B register is performed, and the 16-bit result is available in the accumulator and the B register. So you all know when an 8-bit gets multiplied with another 8-bit, a maximum that it can a result that can expand is still 16-bit. So we will have to have two registers to hold the data. So register A will hold one of the part of it, and register B will hold another part of it. Okay, so in this case, no other registers may be used for this operation. Lower byte of the product is available in accumulator, and the upper byte is placed in register B. Okay, so whenever we can just have an example. Here you can see we are having an example where it is assumed that the original content of accumulator before execution of the instruction was 4 and register B had 8. Okay, so after the execution of this instructions, that is MUL AB, you get 20 hex, and it is actually 32 in decimal, and would be available in accumulator, and the register B would contain 00. Okay, so the lower byte gets stored in accumulator, and the upper byte, which is presently 00, it gets stored in the register B. You see, the initial contents were 04, initial content was 08. After the multiplication, the lower byte is having inside the accumulator, and the upper byte is in the register B. Okay, so in this case, if as the product is not more than FF, okay, so overflow flag would be cleared in this case, and as indicated before, CY flag would always be cleared, and no other flags will be affected. Okay. Now let's move on to the next part where we have the div instruction, that is the division AB, div AB. It offers the scope of dividing two unsigned integers by another 8-bit unsigned integer, both of our value 8-bit. Okay, so in this case, the integer which is inside the accumulator, it actually gets divided by the content of the register B, and the quotient, that is after you divide, the quotient is available in the accumulator, and the remainder will be inside the register B. Okay, so in this case, both CY and the overflow flags are cleared. No other flags are affected. Okay. Now, if we take an example, in this case, assume that the accumulator is having 21 initially. Then we had a 10 hex in register A initially. So that is actually we are dividing 33 by 10. So 33 by 16, sorry. So after doing that, what we have is the accumulator will have the the quotient, and the register B would indicate the remainder part of it. Right. So both in this case, both CY and the carry and the overflow flags will be cleared without affecting any other flags. Okay. Then now the next part is the jump instruction. Now in this case, the jump instruction here, the first instruction that we are considering is jump at the rate A plus dptr. Now, in this case, what happens is the content of the accumulator is taken as an unsigned integer. Okay, to the content of dptr to generate the 16-bit result. Now, initially, suppose it was having 01, accumulator was having 01, and the dptr was having 0200. So they both get added up. Once they added up, it becomes 0201. So it's 0201, which is loaded into the program counter. The program counter content is actually because of the addition of accumulator content and the addition of DPTR, that is the data pointer content, and now it forms the next address, and it points to this particular location. Okay, so neither the previous content of accumulator or DPTR is changed, nor any flag is affected in this particular instruction. So in this case, what we are doing is actually we are adding the content of the accumulator, and we are adding the present content of DPTR, and when those two get added up, the resulting address is loaded into the program counter, and the control automatically switches to 0 to 0 1. Okay, so see, the arrow is from here to here. Why? Because once the 73 was fetched by the control, the program counter was automatically incremented to this. Fine. So after that, after the fetching of this particular instruction, the microcontroller decoded the instruction and was able to understand that it has now encountered a jump instruction at the rate a dptr. So it will add the initial content of accumulator and the dptr, and then move to the designated address, which is shown by the content of program counter. Now let's talk about the swap instructions. Okay. Now swap A. In this swap A, it is again a 1 byte instruction, and it exactly takes one cycle to interchange the content of the upper and the lower nibble of the accumulator. So the accumulator is a 8-bit register. If you separate that, we will get a lower nibble, we will get an upper nibble. So using swap A instruction, what you are actually doing is you are actually moving the lower nibble to the upper, and the upper nibble content to the lower nibble content. So this affects the content of accumulator only. Okay, and the instruction is actually can be compared to the instructions RRA or RLA. Both are possible. Okay, so using RRA or RLA, you can exactly do the same thing what we are doing here. Okay, you can just use four successive RRA or four successive RLA, that is rotate right accumulator or rotate left accumulator. In this case, if you use this instruction four times, the bits starting from MSB will be shifted to this, and after four successive RRAs, the right instructions will be loaded into the upper portion of the accumulator, and so on. And the previous contents will be pushed to the lower side. And the same thing happens if you use RLA. The most significant bit will be pushed to the least and will be pushed inside. And so you get the similar type of action using swap A. Only difference between this is you will require four RRA or RLA, where it will take more time. But just using swap A, you can have one cycle instruction which will execute that in one cycle. Whereas to do the same thing using RRA or RLA, you will require four cycles to complete the instructions. So it will take more time. So in order to manage or optimize your program, you can use the advanced instructions to minimize the required time to do or to a particular function as required in your program. Okay, so this brings us to the end of this lecture about the advanced instructions. Thank you very much